Hello, everyone. Welcome to the first workshop from Izala. I'm Maria Ambrosio. I'm a medical doctor and public health researcher, and today I'll be leading the workshop. So Izala is a online platform that we providing resources, research methods, resources for students and researchers to help them develop their careers. This will also be an online space for discussions about methods. So stay tuned and subscribe to our channel.
And so today we will be discussing the binomial logistic regression model, which is one of the models used in the frequentist statistics. So today we'll start by navigating our research question. So I'll give you a little bit background on the Framingham Heart Study, and then I'll provide the rationale behind our research question and the model that we will conduct by showing you how to conduct a DAG. And then I will discuss a little bit about the logistic regression model. So I want to take some time to discuss the concepts of the probability distribution, the maximum likelihood, odds ratio, and then we will conduct a model, and then we will discuss a little bit about the statistical inference process, and then we will also run a predicted probabilities for more simple interpretation of our results. And I'll end the workshop with some final reflections. And again, if you want to read more about logistic regression, there is this open access book from Craig Sarbark that you can go and read a little bit more about that. And so to start, I like to show you how I organize my files. So you can create this folder, which I called Izala Workshops, which I will be storing all the workshops from Izala. Then you have a folder called Logistic Regression, which you can store your R script file and the HTML file that will be available at the Zala websites, in the future when the website is established. Then I'm going to have a data folder in which I want you to store your data set. So this will make your life easier. I also have here a code for you to download this data set. So this is not real data set. This is a data set from the R package risk communicator. And if you run this code, you'll be able to download the data. And I also have here a piece of code for you to inspect this data. Then you can run this code to write the data set into your data folder. Of course, this is a roughly clean data set. I'm going to have another workshop on data cleaning in which I'll walk you through the steps that I did to clean this data. And so let's talk a little bit about our research question. So today we want to answer, how is coronary heart disease associated with body mass index? So in this workshop, we will use synthetic data that maps the outcomes of the Framingham Heart Study. So it does not contain data on real participants and is strictly for educational purposes. Thus, it should not be used for clinical decisions. So the Framingham Heart Study is a cardiovascular cohort study that started in 1948 in Framingham, Massachusetts, and spans three generations of participants. The study has enrolled 50,000 individuals and collected over 2 million biosamples. The study has been a pillar of preventive medicine, helping us identify the risk factors for heart disease in general. So just to give you an idea, before the Framingham Heart Study, hypercholesterolemia, which is the elevated serum cholesterol, was seen as a normal consequence of aging, and therefore there were no treatments available. But because of major findings of the Framingham Heart Study, we were able to establish important associations like associations between cigarette smoking and heart disease, elevated blood pressure, and increased risk of stroke. And of course, establishing these associations have enabled us to develop preventative measures, public health programs to actually help prevent these conditions and improve the overall health of populations. And so, again, what are we investigating? So, we will investigate how BMI is associated with coronary heart disease. If you have a background in healthcare, you are probably familiar with THD, but I'll provide a brief overview for the broader audience in the channel that is less familiar with the concept. So, coronary heart disease is a term used to describe a state in which the coronary arteries, so you can see here, these are the coronary arteries, the right coronary artery and the left, the branch of the coronary artery. They are unable to supply oxygen-rich blood to the heart muscle, which is the myocardium. You can see this pinky, beautiful structure, which is the myocardium. And so in this state, the heart is unable to supply oxygen-rich blood because of the buildup of fatty substances. You can see these yellow substances are narrowing the way of blood within this artery. But also it may be two reasons like vasospasm, so like the artery is constricted for several reasons. And so like this pipe is not able to supply the myocardium, and as a consequence, the myocardium is not able to pump um, deoxygenated blood to your lungs and oxygenated blood to your body. And you can imagine why this could be problematic. So there is this mismatch on oxygen demand and supply to myocardium. And so I'm not going to talk more about it. There are plenty of resources covering coronary heart disease that you can go and read. I also provide here in the website. I just want to answer like why BMI, why we're looking into BMI as a potential factor and not any other. So there is a rising prevalence of obesity, first of all, and this prevalence is expected to increase the burden of cardiovascular disease among populations across the world. But there's also this so-called obesity paradox that suggests that overweight or mildly obese patients may have better survival after a heart disease event than those in normal weight range. So there is a need for further research to clarify the associations between BMI and coronary heart disease and to examine how this relationship is shaped by sociodemographic factors. So you've seen I took some time to explain why we're doing this, and this is a good step to take when you are, establishing your research question and before you even start your analysis, is understanding why do I want to answer this research question? Has anyone answered before? So at these other workshops, sometimes you see I'll take some time discussing things that are not analysis, that are not code, because I think I want you to experience a little bit the whole process of research that starts by designing a research question and validating that research question. And so to set up your workspace, we will install some packages. I have installed those. You need to install on your site, and I have them here. But before going there, I just want to talk a little bit about the variables that we'll be working with. So today, even though the data set is very large, there are many variables, we will only be working with two demographic, one behavioral variable. So we're going to be working with age, sex, and cigarette smoke per day. We'll use a clinical measurement, which will be body mass index, which will be our explanatory outcome. And our outcome variable will be coronary heart disease, which is a binary outcome that indicates a positive or negative coronary heart disease status. If you want to read more about the other variables in this data set, you can read through the R documentation of the package. And so I'll just copy and paste all of these libraries into my working space, into my source. And if you're using a MacBook, you can just press Command Return. If you're using a Windows, I think it's Control Enter. And we will just read our data set. So read data sets. Here for simplicity, I'll just copy what I have here. Yeah, so you can see in our global environment, we have like around 11,000 variables. I mean, 11,000 participants and 56 variables. But we are only interested in coronary heart disease status at baseline. So we'll only filter baseline participants. So filter baseline participants. So this is a longitudinal data set with 3 time points. So I'm just filtering the first time point, FHS main. I'm saying FHS row. Then I put a filter. And I put steady time point equal 1. And now you can see here we have a shorter, data set. And let me just run the scheme function. It's always a good practice to visualize, what you have in terms of data set. You can open, of course, it in your source, but it's quite hard to visualize like this. So I just prefer to use the scheme function, which, gives you a nice overview of your data set. So right now, everything is basically numeric. It's coded as numeric outcome, so for instance, sex, which is male and female, is also coded as numeric. We'll be transforming this. We can see the proportion of, complete cases or missing data. So for instance, we have around 2% of missing data on total cholesterol and cigarette smoked per day, BMI around like 1% of missingness. We'll also be addressing missingness. Um, yes, but let's now talk a little bit about the assumptions behind our model. So we will draw a directed acyclic graph, a DAG, to visualize our assumptions about the relationships between our variables. So DAGs are useful for mapping potential causal pathways before including variables in a statistical model. So in practical terms, a DAG helps translate a research question into a testable statistical hypothesis. So really nice way for drawing your hypothesis. So when defining a DAG, consider the following question. So what is the outcome or dependent variable? And I'm going to click here. Actually, if you can stop this video and answer those questions on your own, it will be nice. But I would just, for the purpose of time, I don't want to make this very long. I will just read through the questions and then click to reveal the answer. But I will suggest that you stop and try to answer those yourself. So what is the outcome of the dependent variable? So the outcome, remember our research question is how is BMI associated with coronary heart disease status? So the outcome is coronary heart disease status. What is the main explanatory predictor? So it's BMI. Which variables may confound the relationships and therefore need to be adjusted for? Well, we will adjust for sex, age, and number of cigarettes smoked per day because this may confound this relationship. And so just to give you an idea, so let me just read the libraries, Daggity and ggdag. And you'll see how basically, I'm just going to copy. I'll have another video just to cover DAGs and I'll explain every single bit of this piece of code. But basically, I'm using the function Daggity to establish this relationship. So I'm saying that sex contributes or is associated to coronary heart disease status, but it's also associated with BMI. And it's the same for cigarettes per day, cigarette smoke per day, and it's the same for age. And then I'm establishing the main relationship, which is between BMI and coronary heart disease status. And if I run this, all right, and then I can do this, and if I run, I'll have a figure like this displayed. But before displaying the figure, I just want to give you a context. So basically, there are several physiological differences between men and women. So you may ask like why you have this first confounder as being sex. We know that these differences exist and they may influence how BMI relates to the fat distribution and overall cardiometabolic risk. So, for example, men tend to accumulate more visceral fat around the abdominal area of the body, so is associated with a higher risk of cardiovascular disease. Similarly, aging independently increases the risk of coronary heart disease. So in coronary heart disease, reduced oxygen supply to the myocardium occurs because of narrowing of the coronary arteries, remember, and due to reasons such as fatty substances buildup or vasospasms or constriction. So aging contributes to arterial stiffness. So the arteries become stiff, become more narrow, they lose elasticity. There is also reduced nitric oxide that actually contributes to arterial dilation. You also have increased plaque formation. You have higher systolic blood pressure and increased cardiac workflow. So definitely influences the coronary heart disease status. On the other hand, cigarette smoking reduces nitric oxide production, which impairs normal arterial dilation as well and raises blood pressure. And there is also some evidence that heavy smoking is associated with abdominal obesity and higher overall BMI. So remember always that, our hypothesis testing will always start with, a null hypothesis of no association. Let me just show you pretty quick the DAG. How, yeah, so you can see here. So I'm saying that coronary heart disease is associated to BMI is associated with coronary heart disease, but depending on your age can also be associated with coronary heart disease and with BMI. So this is confounding this relationship. The same way, we are saying that cigarette smokes per day can be associated with your coronary heart disease status and with your BMI. Therefore, it confounds this relationship. In the same way, sex can um, be associated with coronary heart disease status and also with your BMI. Therefore, it confounds this relationship. And so we're starting with a null hypothesis of no association. And then we have an alternative hypothesis in which we are saying that, well, there is an association between BMI and coronary heart disease. And so let's do some quick data transformation. I'm not going to spend much time on this because I'm going to have another video just covering the cleaning process, the data. We are checking now if there is any duplicated participant. So using the variable run ID to check for duplicates, and we don't have any duplicates. We are also dropping some of the variables that we're not going to use and those with huge amount of missingness. We are dropping, we're using I created here drop calls object, and I specify the variables or columns that I want to drop. And then I called here in the FHS main object, which will be the main object we're going to use for our analysis. Now we want to recode some of the levels. Again, I'll just copy and paste this here. And now if we take a quick look into our data set, we can see now we have our categorical variables, transformed. So sex is not being seen as a numeric outcome. There are two unique classes, male and female, the same with current smoker. And here we have our numeric outcomes. And just to give you an idea what I did here, so I created like several categories for cigarette smoking per day, for instance. I have a category for non-smokers to very heavy smokers, the same for diabetes status, from normal to pre-diabetes to diabetes. I also create a category for age groups to separate adults from those middle age and older adults. And also I separate participants according to the BMI classification being underweight or classified as obesity. And this classification for um, BMI group actually used the NHS one. Um, and then I just transform these variables as factors. Basically, I'm just specifying what is the lower category, which is non-smoker, and this is the higher category. Now, let's just address missingness. First of all, let's check um, percentage of missingness across the data set. And I run this code. So you can see we have around like a maximum of 9% of missingness, which is like for one of the interaction variables that actually we're not going to use in this analysis. But we will just use like a very simple technique to address missingness. So the missing values in numeric variables we will replace with a mean, and the missing values in categorical variables we will replace with a mode. So this will be a very simple way to retain observation and reduce information loss from incomplete records. In future workshops, I will discuss a little bit more about missingness and introduce you to multiple imputation chain equations as well, which is a more sophisticated approach. But for the purpose of time, I will just use the simple method because I want to spend more time discussing the logistic regression model, um, and then run our model basically. So I'm just, this is numeric. And you see, I'm always like writing a comment because I think it's a good practice for you to always like put a record on of what you're doing. So if someone else come and looks into your pipeline of code, they understand what you're doing. And these are categorical variables. And now let's just visualize pretty quick the study population. So we'll create this object, fhscat long, to change the format of our data set. But right now it's in a white format. So what we're doing here, we're using the pivot longer function, and we are actually taking this columns, current smoker, coronary heart disease status, and we are transforming them into rows, and we are storing them into this column called variable, and then we're creating a new column called values, and then we are storing the values of these columns into this. Again, in the data cleaning workshop, I will discuss a little bit more about this, but I'll just run. And we are just doing this because we want to visualize um, the data set. So I'm using just the ggplot function to plot the categorical outcomes. See, now we can have just like a brief overview of who is this population. I mean, even though this is a synthetic data set, but we want to have like an overview of, the distributions across their characteristics. So we can see we have majority middle-aged adults. We have around, let's say, 4% of coronary heart disease cases. So there's a huge imbalance between coronary heart disease cases and non-coronary heart disease cases. There's a good balance among smokers and non-smokers. Education participants, majority have primary and secondary education, and then we have a majority female. I also did this classification across the BMI groups from underweight to obesity. Okay, for some reason we have some missing values uh, at the obesity. Let me just see. Yeah, and this is mislabeled as well. Let me just see, because I was working on this data set before. Let me just correct this. So this is actually BMI group. I'm actually filling with the BMI group. Actually, I think there's here, but yeah, just forgot to change the labels. And I think the BMI group is also missing from the categorical. Um, so let me just run this again. Let me scheme FHS main. Let me see if the BMI group is Okay, now we don't have any missingness, which is perfect. Now we can plot this again. Let me just run this. Yeah, now it's much better because we had like the missing values also here being plotted. Yeah, so we have the BMI group, underweight to obesity. Um, and yeah, you can see majority middle-aged adults, roughly only 4% of coronary heart disease cases. Proportion of smokers and non-smokers is roughly balanced. Majority of participants with primary and secondary education, and majority female participants. And then we can see the distribution of underweight, normal and overweight and obesity across participants. And again, it's roughly distributed as well. You can see that majority of participants are around like the normal and overweight categories. So you can see here the blue and green. And this is like the same across all categories. So now let's also do a scatter plot to visualize um, how cigarette smoking is correlated with BMI between male and female participants across the coronary heart disease groups, since cigarette smoking will be one of our confoundings. So let me just copy this, run. Yeah, we just a warning message telling us that these are in different, I think, scales, but that's fine. So let's just take a look at it. Yeah, so we can see this like the yellow line is what we are interested in, um, our line of, correlation, um, which is reporting the coronary heart disease cases. And so you can see that we have on the left, we have males. So there's like a slightly positive correlation between body mass index and cigarette smoking. So as the number of cigarettes smoked increases, the BMI also slightly increases. And when it comes to females, this is kind of slightly decreases. But again, it's just correlation. And again, this is synthetic data. We're not using it to make any clinical, inferences um, or conclusions, to seek any clinical conclusions. Also, see the distribution or proportion of the different BMI groups across our data set. I mean, we've seen in the plot before. Let's just first create a count object. They will actually count the different groups. If you see this, you can see, yeah, 44% are fall in the category of normal weight, 41% in the category of overweight, and only 13% falls in the category of obesity. So we can also take a look at the distribution of the numeric variables. So we just say visualize numeric variables. Do this, do this. They are, first of all, in different scales, like for instance, total cholesterol, um, even BMI are in the scales of like hundreds, but then you have this interaction outcomes in the scales of thousands. But we will not address this because the variables we're looking at are basically at the same scale. And so the only thing we will do is center our outcomes to the mean for better interpretation. But it's always good, practice to take a look, at the distribution of numeric outcomes, in case you will include in your model variables that are completely different scales. This is very important. Yeah, and actually you can just run the summary function and call the object containing all the numeric variables. Yeah, you get to just a summary of like the mean. Right, so we have the mean for age, which is 49 years old. The mean for cigarette smoking per day, it's 8 cigarettes. The mean for BMI is 25.85. So now let's take some time to talk about the logistic regression model. And I think at this point, okay, let's not take a break now. Let's just discuss the logistic regression model. And then before we talk about statistical inference, then we can have a short break. So the logit and probit models are regression models used to predict binary outcomes. They differ primarily in their underlying statistical distribution. So logit uses the logistic distribution, which is a sigmoid function, while probit uses the standard normal distribution. Probit is preferred in the economics fields, where latent variables are assumed to have a normal distribution, and the logit is more widely used in the fields like medicine and social sciences. So today we'll be covering only the logit model. So the linear regression model is written as follows. So the outcome y is explained by an intercept beta 0, you can see here, and the combined effect of predictors x1 to xb with coefficients beta 1 to beta b. So your x1s are your variables and your covariates, basically, your explanatory variable and your covariates. And so the logistic regression model uses the log odds transformation to model the binary outcome. So you can see here, the right-hand side of the linear model is the same right-hand side. It's the same as the right-hand side of the logistic regression model. The only difference is the left side. So in the left side, you have the log odds or the logit, which transforms a probability P, which lies between 0 and 1, into a scale that ranges from minus infinite to plus infinite. And log is basically the inverse of the exponential function Euler. So if beta equals to Euler exponentiated to x, then taking the natural logarithm gives log of beta equal x. Remember that Euler's is a mathematical constant with a value approximately equal to 2.71. So this is a sigmoid function. So you can see that at the extreme lower values of your linear predictor, like -4, -6, the probability is kept to 0. It doesn't go below 0. And it has like this kind of, shaped, kind of belly shaped format. And also you see at the extreme values of 4 and 6, it doesn't go above 1. It is contained within 1. So you can only have the probability constrained within the values of 0 and 1. And so the sigmoid function transforms your linear predictor into this conditional probability that the outcome will equal 1, given that the predictor values of x, and in our case, that the outcome is coronary heart disease, given the predictor values of, let's say, BMI, sex, and age. Now let's talk a little bit about the odds ratio. So the logistic model estimates the odds of an event, such as the odds of coronary heart disease status in the exposed group relative to the unexposed group. So for example, if the probability of baseline coronary heart disease in men is 0.30, then the probability of non-coronary heart disease will be 1 minus p, which will be equal to 0.70. So the odds of baseline coronary heart disease in men will be therefore 0.30 divided by 0.70, which will be 0.43. Similarly, if the probability of baseline coronary heart disease in women is 0.20, then the probability of the coronary heart disease will be 1 minus p, which would be 0.80. And the odds of coronary heart disease in women then will be 0.20 divided by 0.80, which will be 0.25. Then the odds ratio for baseline coronary heart disease in men compared with women will be 0.43 divided by 0.25, which will be 1.71, meaning that the odds of baseline coronary heart disease are higher in men. So the key interpretation is that an odds ratio above 1 means increased odds, Odds ratio equal to 1 means no difference in odds, and odds ratio below 1 means decreased odds. Now let's discuss a little bit about the probability distribution. So before defining your model in the frequency statistics, and again, I will have another video discussing a little bit about the differences between the frequentity statistics and Bayesian statistics. But basically, in the frequentity statistics, you are doing your experiment several times over and over again, and you have the assumption that 95% of your experiments will contain the true population value. And I'll discuss this a little bit more when we discuss about the statistical inference and confidence intervals. So before defining the model, it's important to identify three things. Is your data continuous or discrete? What is the range of support? What is the parameters of interpretation? Um, and so I'll have a separate video again discussing more broadly about this aspect for all the types of distributions, but today I will focus on the binomial distribution. So we have the outcome Y for the ith observation that is modeled as a binomial random variable with n trials. You can see here the n trials, and success probability P1. So our binary outcome is reported as having coronary heart disease or no coronary heart disease, or a status of coronary heart disease or status of no coronary heart disease. So it means we're dealing with a binomial distribution. And remember, the binomial distribution models the number of successes in a fixed number of independent trials, where each trial has only two outcomes, such as success or failure. For instance, if you toss a coin, each flip can result in only two outcomes, head or tail. So there's a fixed chance or a fixed probability for heads, which is 0.5, and tails, which is 1 minus p. I mean, if you're dealing with a fair coin. And so which will be also 0.5. So in our example, we have a binary outcome, which is coronary heart disease or no coronary heart disease status. This means that each individual observation will follow a Bernoulli distribution, because remember, in the Bernoulli distribution, your number of trials is equal to 1. It's fixed to 1. And so, and your distribution can only take the values from 0 or 1. But then we are talking about a binomial distribution that this assumption is relaxed. And here, the total number of CHD cases in a sample size of n is modeled as the binomial distribution. So let's now respond to our question. So is our data continuous or discrete? So we have a discrete data because we're dealing with a binomial distribution. And I will also provide a kind of cheat sheet of distributions that will help you. And so what is our range of support? So we know that the support of a probability distribution in statistics is the set of all values where the variable has a chance of occurring. So the range of support for one person row will be 0.1. So the range of support for the binomial count of coronary heart disease cases in n people will be 0 to n. In this case, is the size of our data set, which is what we have around 4,434. So this is our n. So what is the parameters of interpretation? So we have n, which is our number of observations, again, 4,434. P is the probability of a coronary heart disease status. And then we have the linear predictor, which is defined on the log odds scale and then can range from minus infinite to plus infinite. And I hope this is making sense. So now let's discuss a little bit about the maximum likelihood. So for each observation, if the true outcome is 1, the model wants a high predicted probability. If the true outcome is 0, it wants a low predicted probability. So the likelihood is the probability of seeing all the observed outcomes together, given the coefficients. So maximum likelihood estimation finds the coefficient values that maximizes that likelihood. So you can see here in this beautiful plot. So in practice, the model computes values of beta and uses them to calculate the probability P that the outcome variable y equals 1. In our case, our outcome equals a coronary heart disease status. And then uses that to calculate the likelihood of observing the outcome given those values of P. So logistic regression is fitting the coefficients that best explain the observed class labels as probabilities. In our example, we will model the log odds of having coronary heart disease, yes or no, as a function of BMI and social demographics, including cigarette smoking, sex, and age. Each point square in the surface represents a possible set of coefficients. The highest point, peak, is the maximum likelihood estimate. The coefficient values then make the observed coronary heart disease outcome in our sample most probable. So our model finds this peak and returns these coefficients as the best fitting model. And so you can see here, like I have this color kind of set to help you. So the lower probability areas are colored in blue and the higher probability areas are colored in red. And then you have here our point of maximum likelihood estimate. And so now we can run actually our model. But now let's take a 5 minutes break before we jump into running the model.
So now is the time that I invite you to go take a drink, take some tea or coffee, take a 5 minutes walk, and then come back. So we're going to start running our logistic regression model. So welcome back. So now is the fun part where we actually will run our model. So let me just write running the model. So first of all, let's center our continuous outcomes. So these are age, BMI, and cigarette smoke per day. And we want to center them just to make the model intercept more meaningful by expressing it as the expected odds of coronary heart disease for a person with an average BMI, rather than for someone with BMI of 0. So let's center age. So let's center numeric outcomes. I'll just center all of them. And so just main, so I'm calling where let's say BMI centered. This will be the center variable we'll create. It will be equal to BMI minus mean BMI, and then we are not going to include any missing variable, even though we know we have got rid of them, but it's just good practice. And then we also have age center. So I'm gonna actually copy, and then I'll paste. I'll just replace here age. I have age, and then here I have the 6 per day, which is cigarette smoked per day. And also we have a centered outcome for this. And let's run. So now we have these new variables. So if I actually inspect BMI 1, let me just do the summary FHS main BMI centered. I run this. Okay, so there's an error. Let's see. Summary function, the data set, and then BMI centered. Yeah, so now we have a mean 0, and then we have a maximum 30. And remember, our mean for the BMI was like around like 25.85. And now we have centered to mean 0. And so let's first run a very simple model just with BMI as our explanatory variable without any covariates. And one, using the generalized linear model function. And I'm saying I'm using the CHD status variable, which will be explained by BMI. And I'm using the centered variable. And then I'm specifying the family as binomial link. I'm specifying the logit function. And then the data is the FHS main. If I run, then I can inspect my coefficients, FHS 1, which is the first model. So we can see here. So we know that each additional 1 unit increase in BMI is associated with 1.05. Actually, we have to exponentiate first of all. Let's just count, because this now we are looking into log odds, which is 0.05. I exponentiate that. Now we have it. So we know that each additional 1 unit increase in BMI is associated with 1.05 increased odds of baseline coronary heart disease status among the study participants. And again, I'm not saying Framingham Heart Study participants because this is synthetic data. It does not contain data on any real participant. So let's do a second model, which will include our covariates, basically, the potential confounders of our model. Two, again, I'll just copy. And now what I'm going to do, I'll do the plus 6 per day. And I want to use the centered plus 6 plus H twice H centered. And then if I run and inspect coefficients, 2, again, I have here as log odds, which is quite hard to interpret. But what we're going to do is that we're going to exponentiate so we can see the odds ratio. So, HS M2. Now we can see we have a 1.04. Each additional 1 unit increase in BMI is actually associated with 1.04 odds of baseline coronary heart disease status among the study participants. And let's talk a little bit about statistical inference. We also want to know if actually these results are statistically significant, if they contain our null hypothesis of non-association. And remember, for logistic regression, if your confidence interval contains the value of 1, it means that it contains the value of no association. That means our results, if they contain 1, they will not be statistically significant. So you want results that are above 1 or below 1. So let's just see exp. Then we call the function confident, which is the confidence interval. let's first inspect. So let's just see, just run statistical inference confidence interval. And here I'll say model 1. So we know that this is for model 1. And if I do this, FHS M1, so you can see my confidence interval is between 1.02 and 1.08. So I don't have 1, which is a value of no association. So we can say that the results for the model 1 actually are statistically significant. Now let's check model 2. And for model 2 is the same. So X, confident, and then we call the model FHS M2. And then if you run, again, we're interested in BMI. So we don't have the value of 1, even though it's like 1.0004, but it's not 1. Again, this model is statistically significant. But what we can do actually is that we can compare models to see, which model actually is performing better. So we'll conduct the likelihood ratio tests to see what model is fitting the data significantly better. So let's just run likelihood ratio. Okay, run a likelihood ratio test to compare models. And actually, we just call the ANOVA function, and we have FHS M1 compared to FHS M2, and then test equal chi-square. And now you can see, basically, so we have the model 1, and then you have the model 2, basically. And from what we are seeing, the likelihood ratio test suggests that model FHSM2 fits the data significantly better than the first model. So adding the 2 predictors, which is cigarette smokes per day, adding the 3 predictors, cigarettes smoking per day, sex, and age, reduces the model variance by 186.84 points. And also we have a very small p-value showing that this improvement is statistically significant. In other words, sex, age, and numbers of cigarettes smoked per day meaningfully improve our model fit. So let's now combine the coefficients of our model. So we can see the coefficient, the estimate, alongside the confidence interval for model 2. So combine coefficients. So we're going to use the cbind function, exp, and then coef FHS M2, exp, and then use the confident, and then you use the FHS M2. Okay, run. Okay, there's something wrong here. You have to close here. Don't need this. Yeah. So now we can see our coefficient 1.04 and then alongside the confidence interval. Yeah. And so again, we have 95% confidence intervals for, let's focus again on the BMI, which is our main variable. That does not include 1. So it suggests an association between BMI and coronary heart disease, actually a positive 1. However, be careful when you interpret 95% confidence intervals. It is not correct to say that there is a 95% chance that the true population value lies within the specific interval. The 95% confidence intervals indicates that if we repeatedly draw samples of the same size from the same sample population and calculate a confidence interval each time, about 95% of those intervals will contain the true population parameter. Remember, this is a key aspect of the frequentist statistics. The repetition of your experiment with the same population within the same conditions. And then assuming, we have the frequency statistics has this assumption that if you do that, at least 95% of those confidence intervals will contain your true population parameter. So again, be careful when you interpret your confidence intervals. Now let's talk a little bit about the hypothesis test. So we'll use the summary function to produce a compact overview of our model, including the z-value and p-value. Remember that the z-value is the estimate divided by the standard error. So this is your estimate divided by your standard error. And it's based on a normal distribution rather than the t-distribution. And also remember that the z-distribution is the standard normal distribution used when the population standard deviation is known or the sample is large, whereas the t-distribution has heavier tails and is used when the population standard deviation is unknown. It must be estimated from the sample. So in logistic regression, we use z-statistics because the estimated coefficients are maximum likelihood estimates and are approximately normally distributed in larger samples. So when the z-value is greater than 2, so this is the main takeaway for you, it indicates a statistically significant coefficient. However, when the z-value is lower than 2, it signifies a non-statistically significant coefficient. However, the z-value can be biased for larger coefficients, and so we will conduct also the likelihood ratio test to check, the performance of our model, basically. And so let's just run the summary function on our main model, summary, such as M2, if you run it. So we can see we have a z value of 2.25, which is above 1. And again, we have statistically significant coefficients. And so we have a p-value and z-value that are statistically significant. So our p is below 0.05, indicating that the observed association will be unlikely to arise by chance alone. The null hypothesis of no association between coronary heart disease and BMI were true. So in other words, there is less than 5% probability of obtaining this sample regression coefficients if there was no real association between BMI and coronary heart disease. A nice way of reporting these results will be holding sex, age, and the number of cigarettes smoked per day constant. Each unit increase in BMI is associated with 1.04 times higher odds of baseline coronary heart disease among study participants. And then we have the confidence interval reported alongside it. And so let's just conduct the likelihood ratio test. See, over. Which has 2 tests equal LRT. Yes, as you can see here, basically our likelihood ratio test is telling us how much the variances reduce when we, add each one of these predictors. So adding cigarette smokes per day, reduces the variance by around like 0.49. So, so it's not statistically significant. So not much improved in the model fit. But as you add sex, it's reduced by 37.71, and age, it's, improves even more the model fit. The variance is reduced by 148, and it's also statistically significant. So let's also perform some model check techniques such as variance inflation factors and outlier diagnostics. They are important because they help us identify multicollinearity and influential observations that could distort the fitted model and weaken the reliability of the results. For example, if one person in the data set has an extremely unusual blood pressure, for instance, value or value for age, let's say, because have age as one of our predictor, that is higher than everyone else's, that single observation could pull the model in an unrealistic direction. So your linear regression could be, pulled to a direction that is actually not real and make the associations appear stronger or weaker than they really are because of that outlier. So these checks help us see whether the model is being driven by a few unusual cases or by predictors that are too closely related to one another. So let's just check to the multicollinearity check for the library car, run it, and then call the VIF function that stands for variance inflation factor. And this is, so we have like VIF from like 1 point, let's say 02 to 1.15. And as a rule of thumb, values above 5 may suggest moderate collinearity, while values above 10 are often taken as a sign of serious multicollinearity, and that may need attention. But in our case, we don't really need to worry about that. Let's also do the outlying check. So I'm just writing multicollinearity check. And then I'll write here outlying. Outlying check. And if I write influence dot measures such as M2, the dollar sign is dot inf cook e. Then we have some. Again, we have 0 outliers, basically. Another nice thing to compute is pseudo R-squared values. So I'll call the library. I think we have run this library before. So I'll just write compute R-squared values. And R-squared are important to check because they can tell you how much of the proportion of the variation in your outcome, in our case, in coronary heart disease, is being explained by your explanatory variable. And so I will compute several pseudo R-squared techniques. So pseudo R-squared 2, and then which equals C. And I'll just copy this term. So we have the McFadden, the Nagelkirk, and the Cox-Snell techniques. And I like to check all of them, to be honest, since pseudo R-squares are like an adaptation of like R-squared from linear models. So I like checking like different techniques and see the range actually of, okay, let's just call the library, the range of R-squared across them. Um, okay, correctly spelled. Now let's just print the R-square values object. And then you see we have a range of like from 0.4 to 0.12. So the R-square value suggests that BMI explains only a modest proportion of the variation in baseline coronary heart disease status, with values ranging from about 4% to 14%. So the model shows some explanatory power, but BMI alone does not account for most of the differences in coronary heart disease status. Now let's just look into some tables and plots. And I have these functions in my GitHub for the tables and plots. And so this is the library text reg, basically. And for simplicity, I'm just copying this code to here. Yeah, so I'll just write also here, frame table. So I'm using the library text reg. This is a source from my GitHub. I also provide with the code. And then you can see here, basically I have model 1 and model 2, basically. We have the intercept. Again, this is 0.045, but this is the mean of the BMI, because remember we have center BMI, and then we have the values of the slope, which is for the model 1 is 1.05, and model 2 is 1.04, and then we have the confidence intervals displayed like beautifully as well. And we have these values for AIC and BIC. We also have like the log likelihood. And so basically, the goodness of fit statistics show that both AIC and BIC and the variance are lower for model 2 and model 1. So AI places more emphasis on predictive fit and tends to favor slightly more complex models, whereas BIC penalizes additional parameters more strongly and therefore usually favors simpler models. So in both cases, smaller values indicate a better fit when comparing models fitted to the same data. Model 2 also has a higher log likelihood than model 1. And so you can see model 2 has like minus 0.697 and model 1 has minus 0.791. So in general, model 1, it's fitting better our data than model 2, basically. I mean, model 2 is fitting better our data than model 1. And also we can visualize this in a plot. So let's say plot, which is right here. Visualize model 2 plot. I'm gonna use the plot break function. Okay, I'll just copy and then paste it here. And then you can see we run this code already. See the plot that was produced and you can visualize. So basically, just move this to here. As you can see, we have 1 as the line of no association, basically the value of no association. Cigarette smoke per day is around 1, so not significant. You can also see here the labels, and then you can see here the odds for body mass index, which is like around 1.4, as we have seen in our table. And then this lines represent the range for the confidence intervals that is not touching the line of no association. So let's continue. We are almost getting towards the end. Now, let's discuss a little bit about predicted probabilities. Odds ratios are nice to report and interpret, but predicted probabilities are even easier, especially if you're talking to an audience of like non-academics or researchers or policymakers. And so we'll plot the predicted probabilities for the associations between coronary heart disease and BMI across different genders. So this is the code for the plot. And again, I'll just call the library SJ plot, run it, and then I'll say plot model, calling the plot model function. And I'm specifying that I want to use my FHS M2 model type be equal to predictions. When I use predictions, my terms will be, I'm saying that I want to see BMI center. And I also want the values for sex, on the prediction values for those. And then let me just plus, and I'm specifying now the range that I want to see displayed in my x axis, and this is the range for the BMI values. So I'm saying that I want to sequence from 0 to 30 by values of 5, by intervals of 5. And I'm saying the limits as well, which is the 0, 30, and plus, then I'm just giving the coordinates for the y axis. Basically, I'm saying chord Cartesian y lim equals c, and I want to see from 0 to 0.50 basically. And then I'm just specifying the labels. And for the labels, I'm just gonna copy for simplicity. And this is the team. I'm gonna have another workshop. If you want, just put in comments and I will discuss a little bit more about this plot and tables in general. Just move it here, just make it look better. Moving this. So it's nice to have like your code neatly like formatted. Okay, there's something missing here. Let's see what's going on. What have we misspecified? Here we have the scale. Okay. This looks nice. Do this. Okay, probably we have some, see if we have all the brackets. Do you have all the bracket? One bracket is missing here. This is solving everything. Another one for the BMI. Gain. Gain. Sometimes when I want to save time, I'll just copy and paste. Yeah, now let's see our plot. So now we have our predicted probabilities plotted. So we can see that holding all other variables constant, the predicted probability of coronary heart disease increases with center BMI and remains consistently higher for men compared to women. Um, so at a center BMI value of 30 units above the mean, the predicted probability is approximately 13% for men. So you can see this is the mean 0, and this is 30 units above the mean. Again, this is not the real value of BMI. We are now, because we have centered this. So 0 actually signifies, I think, 28.85, which is the mean, and 30 signifies, I think, 56, which is the maximum BMI in our data set. So these are 30 units above the mean. Um, and so we can say that, yeah, the predicted probability is approximately 13% for men compared to 5%. See, 5% in the blue line for women. So these results are actually consistent with the literature suggesting that men have an overall increased risk for coronary heart disease compared to women. And this is explained by several like biological factors, such as like some cardioprotective effects of estrogen in women, in premenopausal women, and the greater visceral fat accumulation in men, especially in the abdominal area. And together with an earlier rise in low density lipoprotein cholesterol in men, and a higher prevalence of risky lifestyle factors like smoking, yeah, among men when compared to women. So all these factors, contribute to a higher prevalence of CHD men when compared to women. And also these lighter lines that you can see in both red predicted probabilities, which is like the men, these are confidence intervals basically. And you can see that these confidence intervals become larger at, the 30 units. It means that actually we have fewer participants at this levels of BMI. And so the fit of our model is actually decreasing. So we have larger confidence intervals. And so to finish, I love to finish with reflections again. Research is an interactive process. This workshops is just to, show you how to run these models and provide you some understanding on these concepts. And also to dismissify some of, this idea that, quant or research is extremely hard is for a specific group of people. I think if you take the time to read and study and also um, spend time with other people doing research, you can learn a lot. You can learn those methods, and this can actually be valuable in your profession, even if you are not a full-time researcher. If you are a healthcare professional, or if you're in social care, for instance, or public health, you run into those studies. You have to read those studies to improve your practice, and I think it's very important that you understand those methods and what's going on behind them. But again, these workshops or these methods are not like a perfect formula for you to say, I'm going to run this and I have the evidence and I have the answer. No, research is an interactive process, as I like to say. And sometimes, in my own experience, you'll be running analysis and a data set and working on a paper for over a year, and you go to conferences, you go to seminars, you talk about your ideas with other researchers, you hear critics about the methods that you are adopting, you have to go and learn new methods, and this is how research works. And for this specific data set, for this specific model, we have identified an association between BMI and coronary heart disease, and we have observed some gender differences. Um, it will be useful to ask another clinically relevant question for instance, at a given age, what is the risk of developing coronary heart disease, or what is the risk of a coronary heart disease status? And does that risk differ according to other predictors, again, such as smoking status, sex, and prevalent comorbidities? So our logistic model estimates the odds of having coronary heart disease at the time of measurement, so at baseline, without accounting for when coronary heart disease occurred. So in a future class, I want to bring a Cox proportional hazards model to examine time to event predictions of coronary heart disease risk, because we have a longitudinal study with 3 time points, and actually will be something interesting to look at. And then we can actually compare the risk among individuals who reach the same actual age during the follow-up. And yeah, I hope this was helpful. Leave your comments, share this video with someone that you know is working with um, a binomial distribution, and is interested in learning more about logistic regression. And I'll also provide, I think I'll have to make available a poll in the channel and in our LinkedIn page to see what methods should I prioritize, because I think I have lots of ideas of methods that I can bring, also including qualitative methods, not only quantitative methods. And because, my time is also constrained, I think it would be nice to hear from you what you want me to cover in future workshops. And again, thank you so much for watching and listening.